grab your pitch black beret and sidle up to our cabaret as we walk the high wire twixt nutrition and knowledge. Listen, Daddy, we gonna contribute to the cell structure in your mind. Marvel as we groove with the vital organs, find folly with the phospholipids. We've intruded upon professors and purveyors of body knowledge, yeah, distilling their syllabi till it seeps from your mind down to paper. Don't forget, they gonna grade ya. Hey now, here they come again. Standard Deviants, knowledge ain't no sin. Welcome to Nutrition News, Nougat-Filled and priced to move. Welcome to the Deviant Groove.
Hi, we're the Standard Deviants, and welcome to the nutty, nougat-filled world of human nutrition. In this tape, we will slice, dice, shake, bake, roast, and puree 10 areas of human nutrition. You know, good old stuff like food choices and human health, nutrition standards and guidelines, the remarkable body, carbohydrates, lipids, protein, vitamins and minerals, water, energy balance and weight control, nutrition and disease prevention. So, let us whet your appetite as you strap on your thinking cap, not to mention your bib, and follow along.
If at any time you're lost or you need to review anything we've said, just reach out for your remote control. You can touch it and pause the tape, you can stop the tape, or you can rewind the tape anytime you want. It's almost real.
This just in, this Standard Deviants video is a healthy supplement for going to class, doing your homework, and reading your textbook. Oh, it is not a substitute for going to class. And now?
Now we know that human nutrition can be pretty tough to swallow. The Standard Deviants have scoured the nation for all the introductory nutrition stuff you need to know. And then hired some cream-of-the-crop nutrition professors to help us. You can count on us to simplify this nutrition stuff and make it go down easy. Believe it, it's our job.
What we're going to learn in this tape is simply how the body reacts to what we put in it. So don't freak out, let's just dive right in.
Part 1. Introduction to Nutrition.
Section A, nutrients.
Let's get started. The first thing you need to know when talking about nutrition is what is a nutrient. Well, a nutrient is a substance found in foods or supplements that your body uses to regulate growth and provide energy, structural materials, maintenance, and tissue repair. In fact, you must take nutrients into your body to maintain optimal health. But before we can go into detail about complex terms like structural material and tissue repair, we need to talk about the 6 basic nutrients the body requires.
The 6 basic nutrients in food are terms we've all heard before: carbohydrates, fats, proteins, vitamins, minerals, and water.
And since you'll have to memorize these 6 nutrients in order, here's a mnemonic device to help you. Just remember this sentence: could Fanny play violin much worse? Part of the reason it's best to learn the nutrients in this order is that the first 3, carbohydrates, fats, and proteins, have a critical difference from the last 3, vitamins, minerals, and water. We'll talk about the differences between these 2 groups in a little bit.
The first 3 nutrients, carbohydrates, fats, and proteins, provide usable energy once they're broken down in the body. The energy they provide can be measured in calories, which we'll talk about in a second. These 3 nutrients are called macronutrients because they make up the body's primary source of fuel.
The last 3 nutrients are vitamins, minerals, and water. Vitamins and minerals, which regulate and control bodily functions, are called micronutrients. The last nutrient, water, is not a micro or macronutrient, but it is the overall vital, numero uno, primo importante nutrient. Water sustains all life processes.
Water is present in almost every part of our body. In fact, we're made up of 58% water.
Okay, so like we said, the first 3 nutrients, carbohydrates, fats, and proteins, provide the energy that makes our bodies tick. Vitamins, minerals, and water, on the other hand, have no caloric value and therefore yield no energy. So what good are they, you may ask?
Well, vitamins, minerals, and water are called regulating nutrients. They just regulate specific bodily functions, but they don't add to or subtract from your weight. That is, you can't gain weight from drinking water or taking vitamins.
Now that we know what the 6 nutrients are, let's talk quickly about calories.
Section B, a quick word about calories.
Now, we've all heard the word calorie before, but when you and I say the term calorie, like how many calories are in a piece of rhubarb pie, we're actually referring to kilocalories. Calories are so small that 1 can of soda provides tens of thousands. And who wants to think in numbers that big? So instead, we measure calories in kilocalories. 1 kilocalorie is equal to 1,000 calories. The prefix kilo means 1,000.
But just like no one wants to go around saying that one soda has 12,000 calories in it, it's also pretty uncool to say things like my soda has 120 kilocalories in it. So just know this. The nutrition guides or food labels report the number of kilocalories in a piece of food. But kilocalorie is such a bulky word, we've trimmed it down and taken it into our everyday language as calorie.
Okay, having said all that, a kilocalorie is the amount of energy a food provides. Like we said, a kilocalorie is simply 1,000 calories. Its abbreviation is kcalorie or kcal. It takes 1 kcalorie of heat to raise 1 kilogram of water 1 degree Celsius. So, now that we have this hip new word, kilocalorie, we'll use it for the rest of the tape to talk about calories.
And by the way, for every gram of carbohydrates you pop in your mouth, you're getting 4 kilocalories. 4 kilocalories of what, you're asking? Well, energy. We'll get to how your body changes a gram of carbohydrates into 4 kilocalories of energy later, when we talk about metabolism. For now, this is all we need to know. And since we've talked about nutrients, let's move on to their distant cousins.
Section C, non-nutrients.
You may be familiar with some of these non-nutrients if you're the type of person who reads all those labels on your food products.
Non-nutrients include substances such as alcohols, organic acids, pigments, additives, and artificial sweeteners. Some of these suckers provide benefits to the body, some are neutral, and others are actually harmful. The important thing to know is that even though non-nutrients provide no nutritional value, some may contain kilocalories.
Ideally, what we want from our diets is to get a high amount of nutrients without consuming too many kilocalories. What we usually mean when we refer to junk food is food that's low in nutritional value but high in kilocalories. Junk food is low in nutritional value because it contains a lot of non-nutrients. Kilocalories that come from non-nutrients are called empty calories because they provide no nutritional value.
Another concern when aiming for nutritional value is avoiding food that is highly processed. Processed food has all those added preservatives and chemicals that you can't pronounce. All those preservatives and chemicals are non-nutrients. A diet that relies on refined, highly processed foods is bad news because it's less nutritious than one which relies on food that's unrefined and lightly processed.
Okay, so let's take a look back and see what we've learned about nutrients. First, there are 6 basic nutrients in food: carbohydrates, fats, proteins, vitamins, minerals, and water. The first 3 nutrients, carbohydrates, fats, and proteins, are called macronutrients and provide usable energy in the form of kilocalories. A kilocalorie is 1,000 calories. The macronutrients make up the body's primary source of heat and fuel. The next 3 nutrients, vitamins, minerals, and water, have no caloric value, but they do regulate many bodily functions. Micronutrients, vitamins and minerals, are present in the body in small amounts. The vital nutrient, water, is present in nearly every bodily function. And finally, a non-nutrient is a substance that may have calories but contains no nutritional value.
Section D, nutrition standards and guidelines.
Nutritional standards in the United States are set by the Committee on Dietary Allowances. This committee makes recommendations for the amount of nutrients needed for each person depending on their age group. These are the guys responsible for those recommended dietary allowances. These recommendations are periodically revised as additional scientific research provides new information.
The most recent revision of the committee's recommendations was in 1989. The recommended dietary allowances, or RDAs as they're commonly called, are expressed for age groups in terms of a specific height and weight. These are median heights and weights and are not meant to be ideal standards.
RDAs are not rigid requirements. They're just guides, but good guides. The RDAs for nutrients are set high enough to meet the needs of all healthy people. They're intended for professional use in community agencies that provide food for needy clients.
In 1992, the U.S. government introduced the food guide pyramid to replace the 4-food group wheel. Instead of reinventing the wheel, they decided to rebuild the pyramid with a fresh design. Let's take a look at it.
The food guide pyramid was designed to encourage all Americans to increase their intake of grains, fruits, and vegetables, while decreasing fat and sugar in their diets. We can all do a little of that, can't we? The pyramid is made up of the 5 food groups and the recommended number of servings from each group we should have each day.
Here are the 5 food groups and daily recommended servings. First, at the base of the pyramid, breads, cereals, rice, and pasta, the largest group, with 6 to 11 servings recommended daily. Second, vegetables, the next largest, with 3 to 5 servings. Third, fruits, with 2 to 4 servings. Fourth, meats, poultry, fish, dry beans and peas, eggs, and nuts, 2 to 3 servings. Fifth, milk, yogurt, and cheese, also 2 to 3 servings.
At the top of the pyramid is an area composed of fats, oils, and sweets. Although people often think of the top of the pyramid as the best, in this case, it's not. It's the smallest. It's also the section we need the least of in our diets. Think of the base of the pyramid as the foundation of your diet. Breads, cereals, rice, and pastas, the stuff we need the most. The stuff at the very top, we need the least. The pyramid indicates that we should consume fats, oils, and sweets sparingly.
One other thing about the pyramid. Note that the fat symbol, the circle, and the sugar symbol, the triangle, are scattered throughout the food pyramid. Those are the naturally occurring fats, oils, and sugars in various foods. That's why we don't need to eat a bunch of junk food and more fats than we need. We already get enough of that stuff in the rest of our diet.
Taken as a whole, the pyramid visually describes 3 important concepts about nutrition: proportion, moderation, and variety. The pyramid suggests proportion by telling the number of servings of each group to consume each day, variety by showing all the different categories of food, and moderation by limiting those foods that are not as good for us. Now, serving size can vary greatly from person to person. That's why we have standard portions depicted in the exchange list system. We'll explain.
In 1950, the American Diabetes Association and the American Dietetic Association developed the exchange list system as a tool for managing the diets of people with diabetes. People who don't suffer from diabetes, however, also use it now. The exchange list differed from the U.S. Department of Agriculture guide by suggesting food exchanges between food groups based on the equivalency of food value and size of portion.
Now that we know about nutrients and the food guide pyramid, we need to know how to plan a healthy diet. The food guide pyramid encourages a total of about 1,600 to 1,800 kilocalories, which is the minimum amount of food needed to meet the RDAs for most adults.
In planning your diet, you should remember 3 things: balance, variety, and moderation. And believe it or not, this is not as difficult to achieve as you might suspect.
For example, a snack consisting of a bean burrito with cheese and tomatoes along with a glass of orange juice includes all 5 food groups. Keep in mind, RDA stands for recommended, not required. Also, remember that dietary allowances don't mean daily allowances. In other words, you're not required to eat the RDA for each nutrient each day. Instead, your overall average consumption should meet the recommendations. Over the course of a week or so, you should achieve balance, variety, and moderation.
Sometimes, even something as simple as reading a food label can be confusing. New on the food labels are calories from total fat and cholesterol, as well as the percentages of their recommended daily value. Dietary fiber is now required on the label as well. This is because these nutrients are the ones Americans should watch most closely.
Now let's focus our attention on what we can do individually to protect ourselves from catching a foodborne illness.
Our greatest risk from food is caused by bacteria. Bacteria either directly invade the intestinal wall or produce toxins that do. One thing you can do to protect yourself is to avoid the possibility of eating foods infected with bacteria. This may seem simple, but did you know that 1/3 to 1/2 of the cases of diarrhea in the U.S. are caused by foodborne organisms?
Yes, it's true. But here are a few things you can do to protect food from being infected by bacteria.
Wash your hands thoroughly before handling food. Wash fresh fruits and vegetables thoroughly. Wash all countertops, cutting boards, dishes, etc. Don't let foods meant for eating come in contact with surfaces that were touched by uncooked meat, poultry, and fish. Cook animal foods thoroughly. Store leftovers in the refrigerator quickly after eating. And keep hot foods hot, which means you shouldn't let a hot meal sit and get cold before you eat it. And cold foods like egg salad or yogurt should be eaten cold. Don't let them sit and get warm.
Now that we know about all the food we're supposed to eat, let's look at what happens to it when it gets into our remarkable body.
Part 2. The Remarkable Body.
Let's take a look at how the body extracts necessary nutrients and transforms food into energy for day-to-day functions. A process near and dear to us, digestion.
Section A, the digestive system.
The process of digestion is both mechanical and chemical. The primary methods of mechanical digestion are chewing and the muscular movements of the gastrointestinal or digestive tract. So, chewing is a form of mechanical digestion, as is the churning process in our stomachs.
Since we all know how to chew, let's look at chemical digestion.
Chemical digestion revolves around hydrolysis. Hydro means water. In hydrolysis, a large molecule is broken down into simpler compounds through the addition of water.
Remember from chemistry that a molecule is two or more atoms of the same or different elements joined by chemical bonds. An example would be water, whose chemical name is H2O. Two hydrogen atoms joined with one oxygen.
And speaking of water, let me explain hydrolysis before we move on with digestion. Hydrolysis is the basis of chemical digestion. What happens is that water, H2O, is split up to make smaller compounds that are easier to digest. The process works like this.
The compounds that make up the foods we eat are broken down into simpler compounds by splitting up and attaching themselves with the elements of water. So one part of the compound will attach to one of water's hydrogen atoms, and the other part of the compound will join up with water's hydroxyl group, OH. Now the larger food compound is broken down into two smaller compounds that are better prepared for digestion.
Compounds are combined atoms, or combined molecules, or combined anything into one unit. We call that unit a compound.
Can we get back to hydrolysis, please?
Sure. Enzymes, substances that bring about chemical changes without being changed themselves, are critical to the hydrolysis process. All enzymes are proteins, but not all proteins are enzymes. We'll talk a ton about proteins in a while, but for now, back to enzymes. They carry out specific tasks in digestion, almost like escorts for other molecules and compounds.
There's a quick way to recognize an enzyme. Most enzyme names end in the suffix ase, sucrase, maltase, etc. We'll talk about these workhorses more later, but for now, let's get back to digestion.
In chemical digestion, hormones are also important. Hormones are the messenger molecules of the body. Hormones are the triggers that tell the organs what's going on so that those organs can kick in and send out the enzymes.
Okay, so let's follow some food from the point it enters the body to the point it, well, exits.
Digestion begins in the mouth. Chewing breaks food up and mixes it with saliva. You know, spit.
Once the chewed food is mixed with saliva, it becomes what's called a bolus. A bolus is just the small ball of chewed food that forms before swallowing.
Swallowing pushes the bolus into the esophagus. But once it's in there, peristalsis, the rhythmic muscular contractions of the gastrointestinal tract, pushes the food down the esophagus. Let's take a look at this process.
First, the food enters the mouth. There, we chew the food and prepare it for its journey into the gastrointestinal tract. We swallow the bolus, and the action of peristalsis pushes it down the esophagus and through a door-like opening called the cardiac sphincter to the stomach.
Once the food is in the stomach, the cardiac sphincter closes behind the bolus to prevent it from re-entering the esophagus. If any food and stomach juices slip back up to the esophagus, then you know what you've got.
Heartburn.
The gastric acids from the stomach irritate the esophagus, causing the burning effect. The stomach continues the digestive process until the food is passed through to a second sphincter, the pyloric sphincter, and into the small intestine.
You see, the stomach is really just a holding tank for foodstuff before it enters the small intestines, where the real digestion takes place. Once the food passes the pyloric sphincter, it goes into the first of 3 segments of the small intestine, the duodenum.
When the food passes into the small intestine, it's in the form of a semi-liquid mass called chyme.
The pyloric sphincter ensures that chyme does not pass back up into the stomach. Thank goodness for the pyloric sphincter, huh? So, let's see if we can keep our sphincters straight. Remember, there are 2 sphincters, and they operate in alphabetical order. That is, the cardiac at the top of the stomach comes before the pyloric at the bottom of the stomach. So, just remember CPs for cardiac and pyloric sphincters.
So food passes through the pyloric sphincter to get to the almost 10 feet of small intestine.
The small intestine has 3 segments, the duodenum, the jejunum, and the ileum. Most of the digestion process takes place in these 3 segments. To remember the order of the segments, just remember the phrase, "Don't jump in."
The small intestine is made up of hundreds of folds. These folds are covered with little projections called villi, and the villi are covered with microvilli. These microvilli increase the surface area of the small intestine for maximum absorption.
Here, enzymes control key chemical reactions that assist in the absorption of nutrients, such as the carrying of nutrients into the walls of the small intestine en route to the bloodstream. These enzyme-assisted processes occur over and over again until all the nutrients are absorbed.
There's another sphincter at the end of the small intestine, the ileocecal valve, that the chyme passes through en route to the large intestine.
Once the chyme is in the large intestine, much of the liquid is withdrawn from it and bacteria digests any remaining food, leaving a semi-solid mass called feces. Here, water helps food speed through the last step of digestion. The final absorption of nutrients takes place in the large intestine. After the nutrients have been absorbed, the feces passes out of the body through the last sphincter, the anus.
In short, food is digested as it moves through the gastrointestinal tract, mainly the small intestine. Along the way, nutrients are passed into the blood and lymph vessels. This process is called absorption. Absorption takes place as nutrients pass through the small intestine villi into the blood and lymph vessels. This is how our body gets the benefits from all the good stuff we eat.
Okay, so let's take another look at digestion. The digestion process works like this. First, remember the process of digestion is both mechanical and chemical. Both forms of digestion begin in the mouth. Food enters the mouth. You chew it up, mix it with saliva, swallow it to form a bolus, and pass it through the esophagus. The bolus is pushed along through the esophagus by peristalsis, the rhythmic muscular contractions of the gastrointestinal tract.
Once the bolus passes through the esophagus, it then passes through the cardiac sphincter. Once through the cardiac sphincter, it enters the stomach and the cardiac sphincter closes so the bolus can't backtrack and give you heartburn. So the bolus enters the stomach and is churned further through peristalsis in preparation for the small intestines. But in order to get from the stomach to the small intestine, the bolus, which is now in the form of chyme, must pass through the pyloric sphincter to get to the small intestine.
The small intestine has 3 segments, the duodenum, jejunum, and the ileum. Once the chyme is in the small intestine, most of the chemical digestion begins. Here, enzymes control key chemical reactions that assist in the absorption of nutrients, such as carrying nutrients into the walls of the small intestine en route to the bloodstream. This happens over and over again until all the nutrients are absorbed. Chyme passes from the small intestine through the next sphincter, the ileocecal valve, to the large intestine. In the large intestine, water absorption helps speed up digestion. What's left of the food after water is absorbed is now in the form of feces and passes through to the final sphincter, the anus. And that's digestion for you.
Part 3. The macronutrients.
Now that we know what happens to food when we eat it, let's look closer at each of those energy-producing nutrients, the macronutrients. Remember from our sentence, could Fanny play violin much worse, that the 3 macronutrients are carbohydrates, fats, and protein.
Section A, carbohydrates.
Carbohydrates are the major energy source for your diet. Foods with high carbohydrate value are starches, sugars, cellulose, and gums made and stored in plants.
Did you say carbohydrates are found in cellulite?
No. Carbohydrates are found in some cellulose products, not cellulite. Cellulose is a dietary fiber that comes from the framework of plants. Examples of cellulose sources are the stems and leaves of vegetables like cabbages, seed and grain coverings like bran, whole wheat and whole rye products, and also apples and pears.
There are two categories for carbohydrates, simple and complex.
Simple carbohydrates are sugars, and the complex carbohydrates are starches and fibers.
Simple carbohydrates are foods like fruits and honey. Simple carbos taste sweet. Some simple carbohydrates, like fruits, are really good for you, while others, like candy corn, are not. Complex carbohydrates are foods like potatoes, peas, and beans.
All right, like we said, simple carbos taste sweet. Why? Well, because they contain sugar. Sugars, which are simple carbohydrates, are either called monosaccharides, mono meaning one, or disaccharides, di meaning two.
Monosaccharides are simple sugars made up of carbon, hydrogen, and oxygen. There are 6 carbons in monosaccharides, and for that reason, they are called hexoses. Just like a hexagon has 6 sides, a hexose has 6 carbons. Monosaccharides are the most important sugars in nutrition because all other sugar combinations are built from them. We'll look at these different sugar combinations in just a second.
There are 3 main monosaccharides, glucose, fructose, and galactose. They're all made up of variations of carbon, hydrogen, and oxygen. The sweetness of a simple carbohydrate depends on the type of monosaccharide it contains. Though it may sound like the name of a ship in a science fiction movie, galactose is a pretty weak sweetener. So simple carbohydrates made from galactose aren't all that sweet. Glucose is the next sweetest monosaccharide, and fructose is mouth-puckeringly sweet.
You may have noticed that all the monosaccharides end in OSE, ose. Remember we said that enzymes end in ASE, ase? Well, the monosaccharide name will end in ose, and the enzyme name that breaks the monosaccharide down will end in ase. For example, galactase breaks down galactose.
Glucose, or blood sugar as it's commonly called, is one of the body's main sources of energy. It's the only sugar that feeds the brain. Often, long-distance runners take glucose tablets or consume sports drinks made with glucose to raise their blood sugar level in the hope of getting more energy.
For most endurance athletes, it makes sense to use glucose supplements if their exercise routine or competition lasts longer than 90 minutes. But for your average athlete, water is just fine. Water is used for the transportation of nutrients through the body and for the overall maintenance of body temperature. Your body has enough readily available stores of glucose for most sports, so water should sufficiently help regulate the process.
Okay, so that was an introduction to monosaccharides, the first type of simple carbohydrate. The other type of simple carbohydrate is a disaccharide. Disaccharides are just pairs of monosaccharides. They're all made up of some combination of glucose and one other monosaccharide. So the disaccharides are all either glucose and fructose, or glucose and galactose. The disaccharide made up of glucose and glucose is maltose. This is also known as malt sugar. Lactose, or milk sugar, is made up of glucose and galactose. And sucrose, or table sugar, the sugar that you put on your cornflakes in the morning, is made up of glucose and fructose.
Now on to the next type of carbohydrate, complex carbohydrates. Complex carbohydrates are called polysaccharides. The prefix poly means many, and polysaccharides are made up of many monosaccharide chains. This is what we meant when we said that monosaccharides are the most important sugars in nutrition. They're the building blocks for all other sugars. There are 3 important complex carbohydrates in nutrition: glycogen, starch, and fibers.
First of all, glycogen is the form in which the human body stores glucose for much of its energy.
Glucose is converted to glycogen and stored in that form in the body. Glycogen is stored in the liver and muscles, just waiting to release all that energy. Whenever we need energy, the glycogen in our liver and muscles is quickly converted back to glucose, which, as we said, is the body's main source of energy.
Glycogen is stored in the form that makes it very easily convertible from glycogen to glucose. Glycogen has many places where saccharide units attach, so they can be broken off easily and used. Just think of glycogen as the human storage form of glucose.
To better understand how this works, let's visualize it. You see, glucose is multi-branched, like this, so it can be broken off for energy at many ends, rather than just at two ends.
The next complex carbohydrate is starch. Starches are a form of glucose stored in plants. Good sources of starch are grains such as rice, wheat, and corn, legumes like peas and beans, and tubers such as potatoes and yams. Each starch molecule contains hundreds of glucose molecules. The last complex carbohydrate we'll look at is fiber. Fiber is the structural part of plants that cannot be broken down by human digestive enzymes, even though most are polysaccharides. Unlike most foods, stronger contractions are needed to move fiber through the GI tract. That may sound like a bad thing, but actually it's a good thing. Fiber is either soluble or insoluble. Soluble fiber aids in the lowering of cholesterol, and insoluble fiber helps with regularity. Or more simply put, some fiber, the more soluble ones, break down in digestion, while others, the insolubles, well, they just pass right through you, to keep you regular. Fiber also contributes to the digestion process by stimulating peristalsis.
That's right. So, even though plenty of water is still needed, fiber helps relieve constipation. Many scientists believe that fiber reduces the risk of colon cancer, and fiber also appears to lower blood cholesterol levels.
Fiber may also be helpful to people interested in weight loss, because high-fiber foods increase the feeling of fullness after meals. Excess fiber consumption, however, may interfere with the absorption of some minerals.
Why is that? Well, being that fiber aids with regularity, it increases the speed of food through the gastrointestinal tract or GI tract. When this happens, food is moving too fast for all the nutrients, like minerals, to be absorbed.
Intestinal discomfort may occur when fiber consumption is first increased, but the body usually adjusts. Be sure to increase your water intake when dietary fiber is increased, or you'll end up with constipation. Whole grain products, vegetables, fruits, dry peas, beans, lentils, nuts, and seeds are good sources of fiber. Typically, Americans consume only about 11 grams of fiber daily. The current recommendation is for 25 to 35 grams of fiber from a wide variety of sources. So get the word out.
One last thing about fiber. When people talk about fiber, they often throw around terms like crude fiber or dietary fiber. The general term fiber has been applied to indigestible carbohydrate and non-carbohydrate substances. But when people talk about the terms crude and dietary, they often use them improperly. So let's not let that happen to you. Listen up. Dietary fiber refers to naturally occurring material in foods, mostly plants, that's not digested. Crude fiber, on the other hand, is what's left over after food's been treated to death in a lab with chemicals with long names.
We've just looked at both simple and complex carbohydrates. Why spend so much time on this stuff?
Good question. Well, carbohydrates are the most efficient form of energy. Each gram of carbohydrates supplies 4 kilocalories of energy. In terms of priority, the body transforms carbohydrates into energy first. So your body really likes this carbohydrate stuff. Most experts agree that 55 to 60% of a person's total food energy should come from carbohydrates.
Excess carbohydrates in the body are stored in two forms. First, as glycogen for energy, and second, as body fat. Carbohydrates also compose parts of many body substances, such as nervous and connective tissue, hormones, and enzymes.
Carbohydrate digestion begins in the mouth. In the saliva in your mouth, there's a salivary enzyme called amylase. This enzyme starts to break down carbohydrates by hydrolyzing them into shorter polysaccharides and maltose.
Okay, so what did all that just mean? Well, like we said, to hydrolyze something means to break it down into smaller compounds by joining up with the elements of water to make it easier to digest. We already learned what polysaccharides are. They're monosaccharide chains. And maltose, well, that's just a polysaccharide made up of 2 glucose units.
From the mouth, carbohydrates move on down to the stomach, where carbohydrate digestion comes to a halt. No significant carbohydrate digestion takes place in the stomach. The mother lode of carbodigestion occurs in the small intestine.
Okay, so we've got these somewhat broken down carbohydrates sitting in the small intestine. What happens next? Well, the pancreas produces several different enzymes that are sent to the small intestine by hormones. The enzymes that the pancreas produces are pancreatic amylase, maltase, sucrase, and lactase. Pancreatic amylase breaks down starches, maltase breaks down maltose, sucrase breaks down sucrose, and lactase breaks down lactose.
The disaccharides are hydrolyzed down to monosaccharides in the small intestine and are carried through the bloodstream to the liver. The liver then converts the monosaccharides to other compounds, usually glucose. Simple sugars raise blood sugar rapidly because their digestion and absorption is quick and easy. That's why we call them simple carbohydrates. But the quick energy that most people associate with simple sugars only lasts for about 20 minutes, and then the energy level drops below where it originally started. That's why you feel a little hyper after eating an entire plastic pumpkin full of Halloween candy, but then a little while later, you feel drained.
Okay, so before we move on to something else, let's take a look at carbohydrates one more time. Carbohydrates are the major energy source for your diet. There are two categories for carbohydrates, simple and complex. Simple carbohydrates are sugars. Complex carbohydrates are glycogen, starches, and fibers. The sugars, which are simple carbohydrates, are either monosaccharides or disaccharides. Monosaccharides are made up of carbon, hydrogen, and oxygen. There are three main monosaccharides: glucose, fructose, and galactose. Disaccharides, the other kind of simple carbohydrate, are just pairs of monosaccharides. Starches and fibers, which are complex carbohydrates, are called polysaccharides and are made up of monosaccharide chains.
Section B, fats.
Contrary to popular belief, we actually need some fat in our diets to keep us healthy. There are three basic functions food fats perform in our bodies. First, they are a fuel source for energy. Second, they supply essential nutrients to the body. And third, they give our food flavor and texture.
First, as a fuel source for energy, food fats supply a basic continuing source of fuel for the body. This allows the body to store and burn fuel as needed for energy. Fats have 9 kilocalories of energy per gram, compared to carbohydrates at 4 kilocalories per gram. This means that when other energy sources are depleted, fat sticks around and continues fueling the body. Not too shabby, huh?
Second, food fats also provide essential nutrients to our bodies in the form of fatty acids. Because they're essential, these nutrients are known as essential fatty acids. Two essential fatty acids, linoleic acid and linolenic acid, are needed to supplement the body's internal supply of fat. Our bodies can't make these fatty acids, but we need them. Most vegetable oils and meats supply us with these two essential fatty acids.
Third, fats also satiate or satisfy the body longer than carbohydrates. Fats also provide some of the flavor in foods. In short, fats may not make us feel as full as fiber or other carbohydrates, but they give us a feeling of satisfaction. They satiate us. Fat.
As some of us know oh too well, there are fats in our body tissues. What we may not know are the 7 functions tissue fats serve. That's right. Those fatty tissues aren't just there to torture us during swimsuit season. There are 7 reasons why tissue fats are good for you. The 7 Tech V10 reasons. Why do we call them Tech V10? Because it helps us remember them. Just take a look.
First, as you all probably know, our tissues are made up of millions of cells. Each of those cells has a cell membrane. Remember all that from 10th grade biology? Anyway, fat is a constituent of cell membranes. In other words, because fat is an important part of a cell membrane, it contributes to the cell structure and therefore contributes to tissue membrane structure. That's where the first T in Tech V10 comes from, tissue membrane structure. But the fats in these membranes aren't just there to lend support. They also help transport nutrient materials and metabolites, the substance produced through metabolism, across those cell membranes.
Secondly, energy is fueled by fat in most body tissue except for the nervous system and the brain, which depend on glucose.
Third, cell metabolism is conducted by fat and proteins known as lipoproteins. These lipoproteins carry fat in the blood to the cells.
Fourth, vital organ protection is provided by adipose fat, which surrounds organs like the kidneys. Adipose fat protects vital organs from mechanical shock and provides a structure for support.
Fifth, thermal insulation is provided by the layer of fat that is directly underneath the skin.
Sixth, essential precursor substances are supplied by fats. By supplying the body with these essential precursor substances, the synthesis of many materials necessary for metabolic functions and tissue healthiness is made possible.
Seventh, tissue fats provide nerve impulse transmission. This is made possible by the tissue fat surrounding nerve fibers for electrical insulation and transmission of nerve impulses.
So you can see, tissue fat is not all that bad.
The chemical class name for fat and fat-related compounds is lipids. All lipids are organic compounds. What's that mean? Well, an organic compound has carbon in it. And lipids, as organic compounds, also have hydrogens and oxygens hanging onto the central carbons that are the backbone of the lipid chain. So, lipids and carbohydrates are made up of the same basic things: carbons, hydrogen, and oxygen.
So let's get a little more familiar with lipids. There are 3 types of lipids: triglycerides, phospholipids, and sterols. Every lipid is made up of fatty acids. There are 2 types of fatty acids: saturated and unsaturated.
When something is saturated, it's got as much of something as it can stand, right? When a fatty acid is saturated, it's got as many hydrogens as there are places for hydrogens to go. The fatty acid is saturated with hydrogens. It's completely hydrogenated. Now, when a fatty acid is missing a hydrogen or 2, it's not as hydrogenated as it could be, and we say it's an unsaturated fatty acid.
3 terms designate the degree of saturation in food fats: saturated, monounsaturated, and polyunsaturated. Let's take a closer look at these 3 degrees of saturation.
First, saturated fats are fats composed of saturated fatty acids. What are they saturated with? Hydrogen, that's right. These food fats mostly come from animals. Second, monounsaturated fats are made up mostly of fatty acids with 2 less hydrogen atoms making 1 double bond. These come mostly from plant sources. Olive oil is an example.
Third, polyunsaturated fats are made up mostly of unsaturated fatty acids with 4 or more places unfilled with hydrogen atoms creating double bonds. These fats come from plants like safflower and sunflower oils. No one fat type is 100% saturated or unsaturated. It's a combination of poly, mono, and saturated fatty acids.
Fats shouldn't supply more than 25% to 30% of the body's well-balanced diet. About 2/3 of these should come from unsaturated fats, or vegetable oils, rather than animal food products or saturated fats.
Remember, all types of fat still have 9 kilocalories per gram. But different types of fat have different effects on blood cholesterol. And depending on the person and their needs, this can be good or bad. If you get more than 10% of your daily calorie intake from saturated fat, the amount of total cholesterol in your body will go up, plain and simple.
Monounsaturated fat should have a minimal effect on total cholesterol in a diet with a 10 to 15% intake of it. If a diet has more than a 10% intake of polyunsaturated fat, it may actually decrease the total cholesterol.
Okay, so now that we know what fats are, let's look at how they're broken down in our bodies for digestion.
All fats have the same basic structure: a fatty acid attached to a glycerol base. You don't need to worry about what a glycerol is. Just know that it's an anchor of sorts that holds fatty acids. If there is one fatty acid attached to a glycerol base, that's called a monoglyceride. If there are 2 fatty acids, it's called a diglyceride. And when a glycerol is attached to 3 fatty acids, you guessed it, it's a triglyceride.
Fat digestion is the process of changing basic fuel fats, like butter, into refined fuel fats that can be burned by the cells for energy. This just means that a food source like fat is broken down to a simpler form like fatty acids. There are several steps in the fat digestion process.
The fat digestion process begins in the mouth, where fat is broken down for passage into the stomach. This is not really a chemical process. You just chew your food into small particles and moisten it for its journey.
The next step in the fat digestion process occurs when the fat hits the stomach. There isn't a whole lot of chemical breakdown of fat in the stomach either. The involuntary act of peristalsis, involuntary muscle contractions, breaks down the fats somewhat. Lipase is the only enzyme in the stomach that specifically breaks down fats. It works on butter fat. While other nutrients of the food mix are broken down by enzymes, fats are separated and made more accessible for the small intestine, which is where the real action is.
The last step in the fat digestion process is when the fat reaches the small intestine. Once fat reaches the small intestine, it begins the process of being chemically broken down. A lipase, which works on emulsified butterfat, breaks apart the triglyceride, separating the fatty acids from the glycerol. Now the fatty acids and the glycerol are small enough to be absorbed. Then, enzymes carry the fat into the walls of the small intestine to begin the process of absorption.
But that sounds easier than it actually is. Fats are difficult to absorb into the bloodstream because they're not soluble in water, and blood is mostly water. Fat, therefore, always needs a solvent carrier. We'll explain soon.
Once in the small intestine, fat is chemically broken down by bile and pancreatic lipase. Let's look at each of these substances and what they do.
First of all, bile is produced by the liver. Once manufactured by the liver, the bile is sent to the gallbladder, which secretes the bile into the small intestine. Bile is an emulsifier. Great, so what does that mean? Well, basically, as an emulsifier, the bile takes the fat that's floating around in the small intestine and breaks it down into smaller chunks. It's important that you realize that this is not a chemical process. The bile isn't digesting the fat or anything, it's just breaking it down into smaller and smaller pieces.
By doing so, the surface area of the fat in the small intestine is increased, giving the enzyme that eventually digests the fat more of a surface area to work with.
Once the fat has been broken down into smaller and smaller pieces, it's time for digestion to begin. The pancreas manufactures and secretes the fat-digesting enzyme, pancreatic lipase. Let's see what happens to a triglyceride that finds itself in the small intestine. Remember from earlier that we told you a triglyceride is a glycerol base with 3 fatty acids attached. The pancreatic lipase then breaks off one of the fatty acids, turning the triglyceride into a diglyceride. The pancreatic lipase then breaks off another fatty acid, converting our diglyceride into a monoglyceride.
Eventually, although it's a pretty slow process, the last fatty acid is broken off and we're left with a lone glycerol. This happens with all the fats that are brought into the body, and we end up with a bunch of fatty acids and glycerols in the small intestine.
Okay, so what's next?
Next, the bile joins up with the newly broken down fatty acids and glycerols and carries them into the wall of the small intestine. Here, the bile drops off the fatty acids and glycerol and says, "See ya!" It heads for the bloodstream where it's taken to the liver and the whole process starts over. Meanwhile, we've got these fatty acids and glycerols sitting in the small intestine. And here's the cool part. There are all these different types of fats that we eat and bring into our bodies, from animals, from plants. Here's where all those different fats are converted into the fat that's used by our bodies. In the wall of the small intestine, the fatty acids and glycerols join back up and make triglycerides, human body fat. Once the triglycerides have been synthesized, they're faced with a bit of a dilemma. Have you ever tried mixing oil and water? It's pretty much impossible because fats are insoluble in water. They won't touch the stuff. That's a problem though, because the triglycerides sitting in the wall of the small intestine need to make it into the bloodstream so that they can be used by the body, and blood is mostly water.
There's no way the triglycerides are going to leave the comfy wall of the small intestine and head for the hills. I mean blood. Something must be done. So, the triglycerides are surrounded by a group of water-soluble proteins. When this happens, they form a spherical complex called a micelle. A micelle carries about 20 fatty acids and monoglycerides into intestinal cells. Now that the micelles have helped them into the intestinal cells, the monoglycerides and fatty acids are reassembled into new triglycerides. Now, these brand new triglycerides and other large lipids are packed into another vehicle called a chylomicron. This protein triglyceride complex is the vehicle that transports lipids from the intestinal cells into the lymph system and eventually into the bloodstream to be put to use by the body.
Chylomicron. This is one popular vehicle. Now, I don't know if you have any triglycerides or large lipids running around at home. I know I do. This baby can sure pack them in. She is a beaut.
By the way, a similar thing happened when the broken down fatty acids and glycerols were sitting in the small intestine. Without getting into too much detail, the fatty acids and glycerols are not only insoluble in the water that's in the small intestine, but they're also repelled by the wall of the small intestine. That's why the bile formed up with the fatty acids and glycerols to carry them into the wall of the small intestine. This is called a solvent carrier system. Now, let's look at the option of fat replacements in our diets.
Food manufacturers are struggling to produce fat replacements that imitate the creaminess and taste of fat without the K-calories. Most of the fat replacements under development are based on one of the 3 energy-yielding nutrients: carbohydrates, fats, and proteins. Carbohydrate derivatives such as dextrins, which are modified food starches and gums, have been used for years as thickeners and stabilizers.
The U.S. Department of Agriculture developed another carbohydrate-based fat replacement called Oatrim from oat fiber. This type of fat replacement can generally be used for baking, but not frying. It can be found in margarine, frozen desserts, and salad dressing.
Olestra is a recently released fat-based fat replacement that is kilocalorie-free. It is indigestible and cannot be absorbed. Olestra carries some fat-soluble substances out of the body. Basically, fat-soluble just means anything that dissolves in fat, like cholesterol and some vitamins. This may result in lower blood cholesterol, but has the potential to interfere with fat-soluble vitamin absorption, like vitamin E absorption. This happens because the vitamins attach to the fat, thinking they're taking the express train to storage, you know, body fat. Fact is, they're on the express train to the toilet.
Simplus, however, is a protein-based fat replacement that was approved for use in 1990. It cannot be used for baking and frying. It is often used in frozen desserts.
The concern with fat replacers is that consumers will use them in addition to other fats rather than in lieu of other fats. If used properly, they may help individuals lower their fat intake while still enjoying the flavors and textures previously reserved for high-fat foods.
Negative effects of fat replacers when eaten in excess include abdominal cramping and diarrhea. That's just what happens when you try to beat nature.
Okay, it's time to step back and see what we remember about fats. First off, another word for fats is lipids. There are 3 basic functions food fats perform in our diets. First, they are a fuel source for energy. Second, they supply essential nutrients to the body. And third, they add to food satiety. Tissue fats also have 7 more Tech V10 functions in our body. Tissue membrane structure, energy, cell metabolism, vital organ protection, thermal insulation, essential precursor, and nerve impulse transmission. There are 2 types of fat, saturated and unsaturated. A saturated fat is a fat that is filled with as much hydrogen as it can take. An unsaturated fat is not as hydrogenated. Fat digestion mainly occurs in the small intestine. Bile and pancreatic lipase are the agents responsible for the breakdown of fat in our bodies.
Section C, protein.
As we said before, protein is a macronutrient that is energy yielding. Now let's take a closer look at this guy.
Amino acids are the building blocks of protein. Chemically speaking, they have a central carbon atom, C, with a hydrogen, H, an amino group, NH2, an acid group, COOH, and a side group. This side group or side chain is the only thing that changes in the chemical structure to make up one of the 20 common amino acids. That makes proteins more complex than either carbohydrates or lipids. Now you know why we saved them for last.
Like we said, there are 20 common amino acids, so the variety of possible sequences is enormous. Most proteins contain at least 30 amino acids, and some may have more than 300. Amino acids are connected to each other with peptide bonds. These amino acid bonds have names depending on the number of amino acids. A dipeptide is 2 amino acids bonded together, while a tripeptide is 3. A string of 4 to 9 amino acids bonded is called an oligopeptide, the prefix oligo meaning few. A group of 10 or more is called a polypeptide, the prefix poly meaning many. Polypeptide chains twist into various intricately coiled shapes.
So why is protein so doggone important? Well, proteins in foods supply the amino acids from which the body makes its own proteins.
Now that we know the structure of protein, let's see what happens to it once it gets into that remarkable body of ours.
Mechanical digestion of protein begins in the mouth where it is crushed and moistened, and chemical digestion begins in the stomach. Hydrochloric acid in the stomach changes protein strands in such a manner that digestive enzymes can break the peptide bonds that hold the amino acids together.
When polypeptides, which are 10 or more amino acids bonded together, enter the small intestine, enzymes hydrolyze them into shorter peptide chains. Enzymes that hydrolyze protein are called proteases. Remember, ase means enzyme. So just take the beginning of protein, prot, and add ase to get protease. A good example of a protease is pepsin, which is released by the stomach and begins to break down the protein into smaller units and amino acids. These cells absorb single amino acids and split groups of amino acids into single amino acids. Then those amino acids are released into the bloodstream to help make protein in the body in order to build tissue.
Now that we know how protein is incorporated in the body, let's look at some of the roles it plays in bodily functions.
Proteins are intimately involved in the growth, repair, and replacement of tissues. Proteins are the building blocks of the human body from the time of conception to death. Proteins are important in most body structures, such as skin, tendons, membranes, muscles, organs, and bones. Enzymes are proteins, and as we said before, they facilitate a wide variety of chemical reactions without being changed themselves.
Proteins are critical in the immune system. Antibodies are large protein molecules that inactivate foreign substances, protecting the body against disease.
Proteins are buffers that help to maintain the acid-base balance of body fluids. They also function as carriers to transport substances such as oxygen throughout the body. And finally, protein, as one of the energy-yielding nutrients, provides some fuel to the body, up to 4 kilocalories per gram.
And when carbos and fats are not good enough to get the job done, in emergency situations that is, you need a tissue-building nutrient like protein to step in and provide energy. Although, I must admit, it may not be the most efficient way to go. Protein provides a modest 4 kilocalories of energy. It works similarly to carbohydrates, but energy is not its main purpose. Building tissue is. 15 to 20% of the K-calories in a healthy diet should come from protein.
Section D, protein quality and protein deficiency.
About 9 of the 20 amino acids are what we call essential. In other words, the body cannot make them, so they're essential to the diet. A complete protein contains the 9 essential amino acids in the same proportion that they're found in the human body. Most animal proteins are complete. Most plant proteins are incomplete.
Overall, plant proteins are of lower quality than animal proteins. This forces vegetarians to combine plant protein foods that are complementary so that the combination supplies the full range of essential amino acids. This is called mutual supplementation or protein combination. It used to be thought that this was critical for vegetarians at every meal. Now it is believed that eating a variety of proteins throughout the day is sufficient.
Proteins that are easily digested are referred to as high-quality proteins. Eggs are one of the most complete and digestible proteins. Therefore, they're an extremely high-quality protein.
The most widespread form of malnutrition is protein energy malnutrition, PEM. This is commonly known as protein deficiency. PEM is common among children in developing nations. In the United States, PEM occurs often among the homeless, the poor, the elderly, and those with addictions to drugs and/or alcohol. PEM leaves individuals particularly vulnerable to infections. These infections and other problems associated with PEM, such as fever, electrolyte imbalances, and anemia, often lead to heart failure even among children.
On the other hand, excess protein consumption offers no known health benefits and may pose health risks. The research is not definitive here. It's difficult for researchers to separate the effects of excess protein from the effects of the excess saturated fat that comes with it. The recommended amount of protein is 0.8 grams of protein per kilogram of body weight. For athletes and people who exercise, however, the recommendation goes up to 1.5 to 2 grams per kilogram of body weight.
Any energy-yielding nutrient in excess, even protein, can contribute to obesity. High-protein diets are rarely successful in sustained weight loss. Okay. What do you call a person who doesn't eat meat?
Vegetarians, baby. A person who does not eat meat is called a vegetarian. Based on what we learned about nutrition so far, it's easy to see that vegetarianism can cause problems when it comes to proper nutrition. Because of that, vegetarians need to be very careful about their diets.
There are different types of vegetarians. Vegans, or pure, strict, or total vegetarians, exclude all animal-derived products from their diets. They consume no meat, fish, poultry, eggs, or dairy products. They only eat fruits, vegetables, and grains. Those vegetarians who consume dairy products but no other animal-derived products are called lacto-vegetarians. Lacto means milk. Remember, milk sugar is lactose. Vegetarians who consume dairy products and eggs, but exclude all other animal-derived products, are lacto-ovo-vegetarians. See the ovo there in between the lacto and the vegetarian? Ovo means egg. Sometimes people are referred to as semi-vegetarians or partial vegetarians if they exclude animal-derived foods such as red meat.
The health benefits of vegetarian diets are many and varied. Although vegetarians are in general healthier, no one can be sure if that's attributed to diet or lifestyle. That is, vegetarians tend to exercise more, use less tobacco, and moderate their use of alcohol. Although it is possible to have a high-fat vegetarian diet and gain weight. So it's not clear to what degree vegetarianism contributes to their commonly healthier body weight, lower blood pressure, and reduced rates of heart disease and cancer.
Vegetarians need to plan properly in order to obtain adequate nutrients. Lacto-ovo-vegetarians, those that consume some dairy products and eggs, do not need to be as concerned about these deficiencies. This diet is safe even for children. Strict vegetarian diets provide the most difficulty for children and pregnant or lactating women. They also risk deficiencies of calcium. Vegetarians need to ensure they obtain adequate vitamin D and vitamin B12 from soy milk and adequate iron and zinc from fortified sources such as breakfast cereals.
Let's go over proteins and vegetarianism one more time to make sure we've got it. Protein is an energy-yielding macronutrient, 4 kilocalories of energy per gram. Amino acids are the building blocks of proteins. Chemically speaking, amino acids have a central carbon atom, C, with a hydrogen, H, an amino group, NH2, and an acid group, COOH. The side group, or side chain, of the amino acid is attached to the carbon atom at the fourth bond. Vegetarians need to plan properly in order to obtain adequate nutrients. Those who eat only fruits, vegetables, and grains are called pure, strict, or total vegetarians. Lacto-vegetarians include milk products in their vegetarian diets. Lacto-ovo-vegetarians include milk and egg products in their vegetarian diets. Semi-vegetarians, or partial vegetarians, are those who exclude animal-derived foods such as red meat, but will include poultry or fish. And that's about it for proteins and vegetarianism.
Okay, so we've looked at how carbohydrates, fats, and proteins work in our bodies. But let's see how they work together in the digestion process. After all, how often are you going to eat a bowl of butter or a loaf of bread by itself? So let's follow some food through the digestive tract and see how all of the digestive organs work together to get the job done.
Suppose you've taken a bite of a ham sandwich. This tasty bite of food contains fat, protein, and carbohydrate. Once in your mouth, you begin chewing the food. Enzymes in the saliva begin to break down the carbohydrate into smaller sugar units, while a pancreatic lipase enzyme for breaking down the fat is released from the tongue. The food bolus travels down the esophagus to the stomach. In the stomach, another lipase is released to work on the fat. So the two lipases now begin to break down the fat into smaller units. At the same time, pepsin, an enzyme which breaks down protein, is released and begins to break down the protein into smaller units and amino acids.
The food next passes into the small intestine where the major digestion and absorption of nutrients occurs. The pancreas releases pancreatic amylase into the small intestine, which breaks down carbohydrates into simple monosaccharides or disaccharides. Special enzymes released from the intestine walls break down the disaccharides into monosaccharides, and these simple sugars are absorbed.
The pancreas also releases lipase into the intestine, which breaks down the triglycerides, molecules of glycerol with 3 fatty acids attached, into separate fatty acids and glycerols. Bile is made in the liver and stored in the gallbladder. When it enters the small intestine, the bile helps the fat become more soluble so the lipase enzyme can do its job of breaking down fats into fatty acids and glycerols. The fatty acids and monoglycerides are now absorbed into the intestinal walls. The pancreas also releases protein-breaking enzymes into the small intestine. These enzymes break down the protein fragments into short peptides and amino acids, which can be absorbed by the intestinal cells.
The absorbed sugars from the carbohydrate enter the bloodstream. The amino acids from the protein travel to the liver through the portal vein, which is the vein that carries blood from the GI tract to the liver, where the amino acids are converted to glucose, fat, or put back into protein structures. In the small intestine, the fatty acids from the fat are packaged into chylomicrons, which take lipids from the intestinal cells into the body. The chylomicrons enter the blood through the lymphatic system. We'll talk about lymph later. Once in the circulatory system, the nutrients can be taken up by various tissues and then used for energy to do work within the cells of these tissues. So much for that ham sandwich.
Part 4. The micronutrients.
Now that we know what happens to the macronutrients when we eat them, let's look at the non-energy producing nutrients, the micronutrients. Remember from our sentence again, could Fanny play violin much worse? This is the violin much worse part, vitamins, minerals, and water. Although water isn't really a micronutrient, it's sometimes included in this group. For now, we'll talk about vitamins and minerals, the true micronutrients.
Section A, vitamins.
The first of the micronutrients are the vitamins. Vitamins are essential nutrients that are needed in tiny amounts. They prevent vitamin deficiency diseases, duh, and support optimal health. We have two categories for vitamins, fat-soluble and water-soluble. Fat-soluble vitamins are trapped in the fat cells of the body and absorbed first into lymph and then into the blood. Water-soluble vitamins are absorbed directly into the blood and are stored in the water-filled parts of the body. The four fat-soluble vitamins are A, D, E, and K.
You can remember the four fat-soluble vitamins with the mnemonic, all dogs eat kittens.
The water-soluble vitamins are the B vitamins and vitamin C.
Like we said, the water-soluble vitamins tend to be absorbed directly into the blood. The fat-soluble vitamins travel first through lymph and then the blood. Lymph is fluid that surrounds the cells that make up the tissues in our bodies. Lymph contains protein and other constituents that have been lost from the blood.
So anyway, most of the sources of fat-soluble vitamins are fats, and fat-soluble vitamins are transported, absorbed, and stored in fats too. The water-soluble vitamins travel freely through the body, while fat-soluble vitamins usually require protein carriers. As far as storage of these two suckers is concerned, the water-soluble vitamins just circulate freely in water-filled parts of the body, while the fat-soluble vitamins are stored in fat cells.
Excess water-soluble vitamins are excreted in urine, while excess fat-soluble vitamins usually remain in fat storage sites. This means it's difficult to reach toxic levels of water-soluble vitamins, but toxic levels of fat-soluble vitamins are likely to occur when they are consumed in excess. So it's necessary to take water-soluble vitamins more frequently than fat-soluble ones, but not daily.
The four fat-soluble vitamins are stored in the liver and adipose tissue until they are needed. You only need to meet the recommended dietary allowance for fat-soluble vitamins over time, not daily, because the body obtains the vitamins from storage as needed. Depending on the amount of vitamins stored in the body, people may go for a period of time with less than their daily intake without becoming deficient.
Toxic levels of fat-soluble vitamins are possible, particularly if people use supplements. Let's look at each of the fat-soluble vitamins. Remember, all dogs eat kittens.
First, vitamin A. The major roles of vitamin A are promoting vision, promoting cell differentiation, maintaining healthy skin, supporting the immune system, and promoting bone growth.
Foods of animal origin are the best sources of preformed vitamin A. These include liver, fish, milk and milk products, butter, and eggs. Plants do not contain preformed vitamin A, but many contain provitamin A, carotenoids.
Carotenoid is just a form of keratin, which is convertible to vitamin A. Chemically, it's a long aliphatic polyene chain composed of 8 isoprene units.
Vitamin A deficiency is a major nutrition problem in developing countries, but it's rare in the U.S. Providing children in developing countries with vitamin A supplements greatly reduces deaths from many infectious diseases.
Beta-carotene is an orange pigment. It's easy to recognize foods with a lot of beta-carotene. They're orange as well. Carrots, pumpkins, squashes, you get the picture. Beta-carotene is a vitamin A precursor. A precursor is a compound that can be converted into a specific vitamin. However, not all dietary beta-carotene is converted into active vitamin A. Some acts as an antioxidant capable of protecting the body against disease. Beta-carotene is the carotenoid with the greatest vitamin A activity, which is to say, it's actively converted into vitamin A a lot of the time. Most foods with vitamin A activity are brightly colored. Therefore, Americans are encouraged to eat dark green and deep orange vegetables and fruits.
Now for the second fat-soluble vitamin, vitamin D. Our bodies can synthesize vitamin D with the assistance of sunlight. Thus, it is not an essential nutrient for our diet. As long as there's sunlight or ultraviolet light around, the special function of vitamin D is to promote normal bone formation. It raises blood concentrations of calcium and phosphorus.
Vitamin D helps direct a complex bone-making and maintenance process that involves many nutrients and compounds. Recent research suggests vitamin D may have other important functions, but these are not yet fully understood.
Those who have a deficiency of vitamin D will develop rickets, a disease where bones fail to calcify normally. But vitamin D is not just important for healthy bones. It also supplies calcium to the nerves and muscles. Vitamin D deficiency affects large numbers of children outside the U.S. Vitamin D deficiency seems to affect underprivileged people the most. One of the common signs of this vitamin deficiency is a rounded, distended belly. That's one reason we often see photographs of malnourished children with bloated bellies.
The range of safe intake of vitamin D is fairly narrow. Supplements should be used very cautiously, especially during times when you're outside in the sun regularly. Excess vitamin D contributes to kidney stones and life-threatening hardening of the arteries of the heart and lung.
Only a few foods supply vitamin D. Liver, egg yolks, fatty fish, butter, and fortified milk are the primary sources. A strict vegetarian cannot meet vitamin D requirements without adequate sunshine, fortification, or supplements. However, most adults do not need to worry about obtaining adequate vitamin D.
People who stay indoors and live in northern, cloudy, or smoggy areas can meet their vitamin D requirement with 2 glasses of vitamin D fortified milk daily. You will not reach toxic levels of vitamin D from prolonged sun exposure alone. However, you do risk premature aging of the skin and skin cancer. So wear sunscreen.
Now for the third fat-soluble vitamin, vitamin E. Vitamin E is an antioxidant, which means that it protects many compounds from destruction by oxidation. Oxidation occurs when certain substances are exposed to and combined with oxygen.
Vitamin E also stabilizes cell membranes, regulates oxidation reactions, and is especially important in the protection of polyunsaturated fatty acids and vitamin A. Vitamin E's antioxidant effect is critical in the lungs, where oxygen exposure is maximal. It protects against air pollutants, especially when engaging in aerobic exercise. It also seems to support the immune response, although at this point we don't really know how it supports it.
A deficiency of vitamin E is rare in humans. Erythrocyte hemolysis, or red blood cell breakage, is the classic sign of this vitamin deficiency. It is most common in premature infants. Toxicity is not as much of a problem with vitamin E as it is with vitamins A and D. Vitamin E is found in green and leafy vegetables, wheat germ, whole wheat products, liver, egg yolks, nuts, seeds, and polyunsaturated plant oils such as margarine, salad dressings, and shortenings.
Finally, the last fat-soluble vitamin is vitamin K. Vitamin K is critical in the process of blood clotting. A deficiency of this vitamin, or any of the other blood clotting factors, results in hemorrhagic disease, which is characterized by excessive bleeding. Vitamin K is also important in the synthesis of bone protein. Vitamin K, like vitamin D, can be obtained from a non-food source. Bacteria in the gastrointestinal tract synthesize vitamin K in the body, but that volume is not sufficient to meet our full requirement.
Vitamin K deficiency is rare but fatal. Vitamin K toxicity is also rare, but possible symptoms include blood cell hemolysis, jaundice, and brain damage. Significant sources of vitamin K, other than gastrointestinal tract synthesis, are liver, leafy green vegetables, members of the cabbage family, and to a lesser extent, milk, meat, eggs, cereal, fruits, and other vegetables.
Now, let's dive into those water-soluble vitamins. First, the B vitamins. They are thiamine, riboflavin, biotin, B6, folate, and B12. These B vitamins help the body use the energy-yielding nutrients, carbohydrates, fats, and protein, but are not actually fuel. Without the B vitamins, however, the body would lack the ability to produce energy. Let's look at each of the B vitamins separately.
First, thiamine is one of the B vitamins used in energy metabolism. It also supports normal appetite and nerve function. Prolonged deficiencies of thiamine can result in the disease beriberi. Symptoms include damage to the nervous system, heart, and other muscles.
Thiamine is in many nutritious foods, especially in pork products and in rich breads and cereals. Excess cooking can destroy thiamine. Using a cooking method such as steaming or microwaving that uses little water will help conserve this and other water-soluble vitamins.
Next, riboflavin. Like thiamine, riboflavin, another B vitamin, facilitates the release of energy from nutrients. It also supports normal vision and skin health. A deficiency of riboflavin may result in a skin rash, inflamed eyelids, and/or cracks in the mouth, and a painful tongue.
Milk and milk products are excellent sources of riboflavin. It is also found in meat, leafy green vegetables, whole grain or enriched breads, and cereals. Light destroys riboflavin. That is why milk is usually sold in cardboard or opaque containers.
Next, biotin, another B vitamin, is important in energy metabolism, fat synthesis, amino acid metabolism, and glycogen synthesis. It is widely available in foods. A deficiency of biotin is rare. Symptoms of deficiency include scaly dermatitis, hair loss, loss of appetite, nausea, hallucinations, and depression.
The next B vitamin, B6, is used in amino acid and fatty acid metabolism and helps to make red blood cells. It also influences cognitive development, immune function, and steroid hormone activity. People who fail to obtain enough B6 will experience weakness, irritability, and insomnia. Untreated, this will progress to growth failure, impaired motor function, and convulsions.
B6 is available in meats, fish, poultry, potatoes, and some green vegetables and purple fruits. Heat destroys B6. Unlike other water-soluble vitamins, excess B6 is stored in the muscles and not simply excreted in the urine. This means it can reach toxic levels. Symptoms of toxicity include bloating, depression, headaches, and irreversible nerve damage.
Some people take B6 to cure carpal tunnel syndrome, sleep disorders, or premenstrual syndrome, PMS. However, self-prescribing can be hazardous to your health and is not recommended.
Another of the B vitamins, folate, is also known as folic acid or folacin. Its primary purpose is DNA synthesis. Therefore, it is important in new cell formation. Research has focused on the relationship between folate and the prevention of neural tube birth defects. These defects occur in the early stages of pregnancy, often before the woman realizes she is pregnant.
That's why the Public Health Service recommends that all women who are capable of becoming pregnant take 0.4 milligrams of folate daily. This is the first time the Public Health Service recommended a dietary supplement for the general population. If women ate the recommended minimum 5 servings of fruits and vegetables daily, supplements would not be necessary. But many women only consume about 0.2 milligrams of folate in their daily diet. If you think of foliage when you think of folate, you will be able to identify a major source of folate, leafy green vegetables like asparagus.
Another B vitamin is niacin, which is also known as nicotinic acid. Niacin is a partner with riboflavin in converting proteins and a small amount of glycerols from fats to glucose for the eventual release of energy. Lack of niacin is connected with the disease pellagra, which is characterized by dermatitis and failure of the nervous system. Pellagra can be fatal. Good sources of niacin include most meats, peanuts, dried beans, and peas.
Finally, the B vitamin B12 is used in new cell synthesis. It helps to maintain nerve cells and helps to break down some fatty and amino acids. A deficiency of B12 results in a disease called pernicious anemia. The symptoms include large cell type anemia, a smooth tongue, fatigue, and degeneration of nerves leading to paralysis and hypersensitivity of the skin. Excess consumption of folate can mask pernicious anemia. B12 is readily available in animal-derived products. Vegans need to be sure to obtain adequate amounts from supplements or fortified foods.
The water-soluble vitamin not in the B family is vitamin C. Vitamin C, also called ascorbic acid, is essential in collagen formation. Collagen is the protein that provides firmness and support to tissue cells. Think about all those skincare products that contain collagen to firm and tone your skin, promising younger-looking skin. Like vitamin E, vitamin C is an antioxidant, which means it prevents the destruction of cells. It also strengthens resistance to infection, plays a role in thyroxine synthesis and amino acid metabolism, and helps in the absorption of iron.
Citrus fruits and their juices are excellent sources of vitamin C. Broccoli, tomatoes, strawberries, cantaloupe, guava, mango, papaya, and peppers are also good sources.
Vitamin C deficiency disease is called scurvy. It used to be a big problem for sailors who didn't have access to fresh food for long periods of time. Therefore, the British Navy started supplying lemons and limes to their sailors to prevent scurvy.
Symptoms of scurvy include bleeding gums, loosened teeth, rough skin, blotchy bruises, and failure of wounds to heal. Claims that large amounts of vitamin C can prevent or cure the common cold have not been substantiated. The only research evidence to support those claims shows that those who took vitamin C supplements had colds that were 1/10 of a day shorter. That translates into 2.5 hours shorter. Not exactly a big deal for most cold sufferers.
Speak for yourself.
It is possible to ingest too much vitamin C. Excess consumption increases the risk of kidney stones, diarrhea, abdominal cramping, the destruction of vitamin B12, and interference with anti-clotting drugs.
Let's look at these vitamins once more before we move ahead. Vitamins are micronutrients. They prevent deficiency diseases and support optimal health. There are two kinds of vitamins, water-soluble and fat-soluble. The water-soluble vitamins tend to be absorbed directly into the blood. The fat-soluble vitamins travel first through lymph and then the blood. The fat-soluble ones are A, D, E, and K. The water-soluble vitamins are the B vitamins and vitamin C. The major roles of vitamin A are promoting vision, promoting cell differentiation, and supporting the immune system. The major role of vitamin D is to promote normal bone mineralization. The major role for vitamin E is as an antioxidant, which means that it prevents the destruction of cells. The major role of vitamin K is to promote blood clotting. The B vitamins are thiamine, riboflavin, biotin, B6, folate, and B12. These B vitamins help the body use the energy-yielding nutrients like carbohydrates, fats, and protein. And vitamin C, or ascorbic acid, is essential in collagen formation.
Section B, minerals.
The second of the two micronutrients are minerals. Minerals are inorganic elements, which means that minerals don't come from plants or animals. The two major functions of minerals are, first, building body tissue, and second, regulating body processes. Minerals such as calcium, phosphorus, magnesium, and fluorine contribute to bone tissue quality.
Minerals are not of plant or animal origin, and although they're essential, minerals are needed in small quantities. There are two categories of minerals based on the amount needed daily. The first, macrominerals, are those needed in quantities of 100 milligrams per day or more. The second, microminerals, are needed in only very small amounts. Macrominerals include calcium, chloride, magnesium, phosphorus, potassium, sodium, and sulfur.
Next, the microminerals or trace minerals are needed in very small amounts. The essential trace minerals are iron, iodine, fluoride, selenium, zinc, manganese, cobalt, copper, molybdenum, and chromium. Be careful when it comes to magnesium and manganese. The first one, magnesium, is a macromineral, while the second one, manganese, is a micromineral.
Minerals are required in many essential compounds that regulate bodily functions such as hormones and enzymes. Dissolved minerals are responsible for nerve impulse transmission and muscle contraction.
The recommended dietary allowances do not include all known minerals. There are recommendations for calcium, phosphorus, magnesium, iron, zinc, iodine, and selenium only. This is because minerals interact with each other and our knowledge is incomplete about the usefulness of all minerals.
Now, let's look at each of the macrominerals.
First, calcium is the most abundant mineral in the human body. In addition to its critical role in bone and tooth formation, calcium is also needed for blood clotting, permeability of cell membranes, transmission of nerve impulses, contraction and relaxation of muscles, enzyme activation, and absorption of vitamin B12.
Second, phosphorus is significant in bones and teeth. It's also required for energy metabolism, enzyme formation, acid-base balance, and the absorption and transportation of fats and fatty acids.
Third, sodium is another essential mineral. Although we usually only hear about the health risks associated with consuming too much sodium, it's required for life. Sodium is needed to transmit nerve impulses, to aid muscle contraction, to maintain fluid balance in the body, and to promote glucose absorption and cell permeability. The American diet is loaded with sodium, so meeting the recommended minimum intake is not a problem. It's excess sodium that's the problem.
Fourth, potassium works with sodium to maintain an appropriate fluid balance in the body. Some Americans have been known to deplete their potassium levels through excess consumption of alcohol. Alcohol is a diuretic and may result in the kidneys excreting too much potassium. This situation can be corrected by consuming some potassium-rich foods, such as bananas or orange juice, or maybe just drinking less alcohol. Potassium is also used for nerve impulse transmission and muscle contraction, energy metabolism, glycogen and protein synthesis, and blood pressure maintenance.
The last three macrominerals, magnesium, chloride, and sulfur, work in conjunction with other minerals. Magnesium activates energy and mineral metabolism. It also helps regulate nerve stimulation and muscle contraction. Chloride assists in maintaining the water and acid-base balance. It's also a requirement for the hydrochloric acid used in chemical digestion in the stomach. Sulfur is a component of the protein in every cell. It's obtained through the consumption of protein, and it also smells really bad, like rotten eggs.
Now let's look at the microminerals, or trace minerals.
First, iron. The fact that iron is a micromineral may lead you to underestimate its importance. A small volume of iron performs critical functions. Iron is part of the compound hemoglobin that carries oxygen from the lungs to the cells of the body.
If the body's need for iron is not met, anemia may result. In this situation, the oxygen needs of the body tissues are not met, resulting in paleness, lethargy, and fatigue.
Next, iodine is required for normal functioning of the thyroid gland. This gland produces hormones for energy metabolism, growth, and development. Most people use iodized salt to obtain adequate amounts of iodine. Insufficient iodine intake often manifests itself in the formation of a goiter, an enlargement of the thyroid gland that swells in the neck.
The next micromineral, fluoride, is used interchangeably with the term fluorine. Fluoride is a component of bones and especially teeth. Many areas fluorinate their water supplies, reducing tooth decay by 50 to 60%. Excessive fluoride can cause spotting of the teeth and bones, as well as kidney, muscle, and nerve function damage.
Other trace minerals perform important functions in the body. Selenium is essential for the proper functioning of the thyroid gland. So if you don't want a goiter, don't short yourself on selenium. It's also important for proper functioning of the heart. Zinc plays a role in protein synthesis, carbon dioxide transport, and use of vitamin A. Manganese is important in blood formation and tendon and bone structure. Cobalt plays a part in red blood cell formation. Copper is required for iron use. Molybdenum is involved in the metabolism of fats. And chromium is necessary for normal insulin activity, which regulates blood sugar levels.
Okay, so let's take another look at minerals. Minerals are inorganic elements and they have two major functions. First, they help build body tissue, and second, they regulate body processes. Necessary for proper nutrition, minerals are divided into two categories, macrominerals and microminerals. The macrominerals are needed in quantities of 100 milligrams per day or more. The macrominerals include calcium, chloride, magnesium, phosphorus, potassium, sodium, and sulfur. The microminerals, or trace minerals, are needed in very small amounts. The essential trace minerals are chromium, cobalt, copper, fluoride, iodine, iron, manganese, molybdenum, selenium, and zinc. Minerals are required in many essential compounds that regulate bodily functions, such as hormones and enzymes. Dissolved minerals are responsible for nerve impulse transmission and muscle contraction.
Supplements in the United States are big business. This industry grosses approximately $4 billion a year. But foods still have much more nutritional value than supplements. Some people, however, find it impossible to obtain their needed nutrients from food. In such cases, a multivitamin can be used. When choosing a multivitamin, two major things to consider are form and content.
First, let's look at form. When choosing a multivitamin, you have the opportunity to select the form you prefer, chewable, liquid, or pill. You'll want to select a brand that meets the U.S. Pharmacopoeia, or USP, guidelines, which suggests that supplements should completely disintegrate within 30 to 45 minutes. The USP establishes standards for quality, strength, and purity of supplements.
The second thing to check when choosing a multivitamin is its content. Make sure that the multivitamin has the vitamins in the proper dosages that you need.
As far as content is concerned, you will want to select a supplement with vitamins and minerals in amounts that are less than, equal to, or very close to the RDA. Do not select supplements that provide more than the RDA of vitamin A or D or any mineral. Avoid any supplement that provides more than 10 times the RDA for any nutrient.
Except for menstruating women, doses of iron should not exceed 10 milligrams. In general, avoid high doses. Remember that more is not necessarily better. The RDA is plenty. Excess vitamins and minerals can be just as devastating as insufficient quantities.
Think of it this way. If it's cold outside, I'd tell you to wear a hat, coat, gloves, and scarf. And if you wanted to be a little warmer, I'd tell you to put on some long johns first. Now, if I wanted you to be healthy, I'd tell you to eat 4 to 6 small meals a day. And if you wanted a little extra help, I'd tell you to have a multivitamin that doesn't exceed 100% of the RDA.
What would happen if you go outside in just your long johns, you may ask? Well, you freeze your butt off. You see, the long johns don't replace the hat, coat, and gloves, just like the vitamin and mineral supplements don't replace the 4 to 6 small healthy meals. You see, the long johns supplement your outerwear, just like the vitamins supplement your meals, hence the name. Got it?
I got it. Now try to ignore the fantastic claims and attractive packaging of vitamin supplements and focus on the form, content, and price. Remember, the RDA provides guidelines for all necessary nutrients. Local or store brands often cost a lot less than national brands, and they usually contain the exact same ingredients.
Now that we've covered both the macro and micronutrients, it's time to cover the last nutrient. It's neither macro nor micro, it's water.
Part 5. Water.
Section A, the functions of water.
On a scale of things that are important to our survival, oxygen comes first, water is second.
That's true. It's impossible to survive more than a few days without water, but a person can survive for weeks without food. Your body weight is 50 to 75% water. Every cell in our bodies contains water, but unlike camels, our bodies can't store water.
An average adult needs 1 milliliter of water per calorie consumed. Infants require 1.5 milliliters per kilocalorie. An average adult who expends about 2,000 to 2,500 kilocalories per day would need about 2 to 2.5 liters of water. 5 to 6 cups of that water, 1.2 to 1.5 liters, should be from fluids, but the remainder may come from water that is found in food and something called metabolic water, which is the water you get when energy-yielding nutrients are broken down.
The amount of water you need on a day-to-day basis may vary due to environmental conditions and physical activity. People engaged in heavy physical activity at high altitudes require more water. Living and working in hot environments increases required water consumption, especially if accompanied by high humidity. And for women with newborns, breastfeeding also increases your need for water. Also, people who don't drink much water have an increased need for water.
Water is the main substance that makes up blood, lymph, and body secretions. Chemical reactions occur in water, and sometimes water acts as a catalyst. A catalyst speeds up chemical reactions or allows them to occur under otherwise impossible conditions.
Section B, water balance.
Normally, fluid intake and output should be in balance. A healthy person does not gain water weight from drinking excess water. If a person is dehydrated and then drinks a lot of water, it may appear like they gain weight, but they don't really. The body excretes what it does not need. Water balance is the balance between water consumption and water loss. In general terms, water balance equals intake minus output.
The amount of fluid in the body is tightly controlled because imbalances can be lethal. The body fights to retain balance by adjusting both intake and excretion as necessary. The hypothalamus is the brain center that controls the maintenance of water balance and regulates body temperature. It detects if the blood is too concentrated and therefore low in water.
Thirst is not a reliable indicator of when to drink water. If you're thirsty, then you're already low. As a minimum, the body must excrete about 500 milliliters of water daily as urine to get rid of metabolic waste products. Water is also lost from the lungs as vapor and from the skin as sweat, and there's also some lost in the feces. To keep an appropriate water level, 6 to 8 glasses of water per day is recommended as a minimum.
Water balance maintains blood volume. Blood volume affects blood pressure. If blood volume falls, then blood pressure is reduced as well.
Now that we know what water balance is, let's look at what happens when our water balance is low.
Dehydration is an excess loss of water. It develops through either lack of water intake and/or excess water loss. You can check the level of hydration by noting the color and volume of urine. The lighter the color, the better hydrated you are. However, if you are taking vitamin B or C supplements, you may note a slight darkening of your urine as the excess vitamins are excreted. Dark yellow, odorous urine generally indicates that fluid consumption should be increased. You should produce clear urine at least 5 times a day. If your urine is dark, you need to drink more water.
Dehydration in a hot environment may lead to heat exhaustion and eventually to a life-threatening condition called heat stroke. People at greatest risk for heat stroke are the elderly because their bodies don't regulate fluid well, the chronically ill because they may have disrupted fluid balance, low fluid intake, excess fluid excretion, kidney problems, or diuretic medication, and lastly, alcoholics because they're consuming alcohol, which is a diuretic.
Heat stroke is more deadly than any foreign enemy. Seriously, some experts believe heat exhaustion should be renamed severe dehydration because that's really what it is. Symptoms are flu-like and include severe thirst, fatigue, headache, nausea, vomiting, and sometimes diarrhea. There may be a slight increase in body temperature as well.
A water loss of more than 6 or 7% of body weight is life-threatening. Infants become dehydrated most quickly because their bodies contain a higher proportion of water. When infants have diarrhea, fever, vomiting, or other conditions which cause water loss, it can pose a serious problem that may require intravenous fluids to correct.
That's water for you. What's next?
Part 6, Energy Balance, Weight Control, and Metabolism.
Energy is not produced, but is transformed in the body. The kcalories, or stored energy in food, is released when we digest it. And the main source of energy in the world is the sun.
Our bodies have 4 basic forms of energy: chemical, electrical, thermal, and mechanical. But first, let's look at the big picture, the place where all energy begins, the sun.
The sun releases energy into water, air, and plants. Plants grow from the sun's energy, animals eat the plants, and we eat the plants and the animals. That's how we get food energy from the sun. Once stored chemical energy in food is taken into the body, it's converted into several other forms of energy. Mechanical energy is used for muscle contraction. Electrical energy is used for brain and nerve activity. And thermal energy is used for the regulation of body temperature. Energy is then released from the body as heat, which dissipates into the atmosphere. Basically, chemical energy allows all the other forms of energy to happen. So let's take a look at chemical energy, the daddy of all forms of energy in the body.
For the sake of this tape, chemical energy will be the form on which we'll focus. Chemical energy is directly linked to the transformation of food into energy in the body.
You see, chemical bonding is the catalyst, the primary mechanism that controls the transformation of energy in the human body. When something chemically bonds, it does what it sounds like it does. It holds the elements of compounds together with bonds. These bonds contain energy. When these compounds are consumed by the body and bonds are broken down, the bonds release that energy to be used for bodily functions.
There are three types of chemical bonds in our bodies: covalent, hydrogen, and high-energy phosphate bonds.
First, covalent bonds are the strongest bonds around, even stronger than U.S. savings bonds.
Second, hydrogen bonds are weaker than covalent bonds, but they can form bonds in high numbers. The fact that they're less strong is significant because they can be broken down to transfer energy more easily.
And third, high-energy phosphate bonds are important because they form energy to be stored for later use. They're necessary for the body's ongoing energy needs, including cell work. The main compound formed through this bond is adenosine triphosphate, or ATP, which is important because this is the stored energy within muscles used for fight or flight. But it's only enough energy stored to last a maximum of 10 seconds.
Okay, now that we know what type of chemical bonds we have, let's get back to the issue at hand, chemical energy. Controlled reaction rates help regulate chemical reactions. What's that mean? Well, some reactions need to be sped up or else they would span several years. Others need to be slowed down or else they would explode in an instant.
There are three control agents that regulate reaction rates: enzymes, coenzymes, and hormones.
Enzymes are proteins that make chemical changes without being changed in the process. Enzymes in every cell control specific cell reactions, and specific genes control the production of specific enzymes. Keep in mind that there are thousands of genes in each cell making proteins and enzymes.
Each enzyme works on its own specific substance. This specific substance is called the enzyme's substrate. Think of the enzyme and the substrate as a lock and key that, well, fit together. So, this enzyme goes around in the cell looking for its substrate, causing these reactions, all the while remaining unchanged itself. The original enzyme always remains the same and is ready to perform specific tasks again and again.
Enzymes don't do all this work on their own. You see, enzymes need partners to perform these tasks. These partners come in the form of the coenzyme. The prefix co indicates that it works in conjunction with the enzyme. When the work is done, the coenzyme is changed or reduced, unlike the enzyme, which stays the same.
And finally, the third control agent that helps regulate chemical reaction rates is hormones. Hormones act as messengers to trigger or control this enzyme reaction. Now that we've given you the basics on energy balance, let's take it a little deeper and get into the technical stuff.
Remember, carbohydrates, fats, and proteins are the three nutrients that provide us with energy. Once the single sugars from carbohydrates, the fatty acids from fat, and the amino acids from protein are brought into the cell via circulation and other transport mechanisms, they can be broken down or metabolized to get energy. Ultimately, carbohydrates, fats, and protein are metabolized to form adenosine triphosphate, or ATP, and ATP is what the cell uses for energy.
There are several biochemical pathways used for the formation of ATP. Some of them require oxygen, which means they're aerobic. Others don't require oxygen and are anaerobic.
Aerobic metabolism is where oxygen is required in the chemical reactions to form ATP. To get energy from fatty acids, you need to have oxygen-available aerobic metabolism. The same for amino acids. But with sugar, you can get energy with or without oxygen, so aerobically or anaerobically.
Let's start with carbohydrates, or the simple sugars. Basically, here we're talking about glucose. The glucose molecule first goes through a series of 10 chemical reactions. Each reaction is controlled by a specific enzyme. By the time glucose passes through these 10 reactions, it's now 2 molecules of pyruvic acid, or pyruvate. In the process, 2 ATP were formed. These ATP now can be used in the cell for any job that needs energy. No oxygen was required to produce these ATPs, so this is an anaerobic metabolism.
But we aren't done yet. If there is oxygen available and other conditions are right, then the 2 pyruvates will continue through a series of reactions, each controlled by an enzyme, until all that is left is water, carbon dioxide, and more ATP. Hence, the end products of carbohydrate or sugar metabolism are water, which the body can use, carbon dioxide, which we exhale into the atmosphere, and ATP, that we can use later to get energy to do work.
With fatty acids, it's a little different. Since the fatty acid is a string of carbon atoms hooked together, the first step is to break these apart into smaller pieces. The fatty acid goes through a series of chemical reactions that break off smaller bits, each containing only 2 carbons. These small fatty acid bits are called acetyl coenzyme A. The acetyl coenzyme A now enters the same cycle of events, or chemical reactions, as our sugar did once it got past pyruvate. Basically, the fate of fat is the same as sugar. Fat, however, didn't go through the 10 anaerobic reactions that sugar did, so fat can only be used for energy when oxygen is present.
We're just trying to explain how the body uses energy from carbohydrates, fats, and even proteins. The same holds true for amino acids. Proteins or amino acids bypass the anaerobic reactions and enter the scheme of things at either acetyl coenzyme A or a bit further down the line.
So now let's try and clear up a few myths about being overweight.
Section B, weight control and metabolism.
We all need body fat for survival. Men need at least 3% body fat, and women need 12% just to survive. When people starve to death, they die from fat loss, not protein loss, which only emphasizes how important fat can be in one's life. More than likely, starvation victims die from colds or the flu due to a weakened immune system. As you can see, I'm a survivor.
But body fat can become a problem. Bodies that are obese are those where 30% of the body weight is fat. That's why the proper term for someone who has more fat weight than he should is overfat, not overweight.
Being overweight is not the same as being obese. A person can be overweight for their weight-to-height standard, but their weight may not be made up predominantly of fat. You might weigh more than the healthy standard for your height, but that alone doesn't mean you're fat, just overweight. Most football players or bodybuilders are an example of this. They're often overweight, but not necessarily over-fat.
Laboratory studies have shown as a basic model that the adult body is made up of 20% lean body tissue, which is called lean body mass, or LBM, 25% fat, approximately 50% water, and 5% mineral mass. Of course, these percentages vary from person to person.
LBM, or lean body mass, is the active fat-free cells that largely determine the basal metabolic rate, a term we'll define in a few minutes, and the body's need for energy and nutrients. Another way of looking at LBM is that it's everything in the body but fat, mostly tissue substance. We'll talk about metabolic rates later, but for now, just remember that lean body mass determines the basal metabolic rate. When people lose weight by altering their diets alone, they lose lean body mass as well as fat, which isn't good. The best thing to do when you want to lose weight is a combination of dieting and exercise. Exercise will help you lose body fat while maintaining lean body mass.
Body fat varies from person to person due to age, climate, diet, exercise, genetics, and fitness. About half the body's fat is subcutaneous, the fat that's right beneath the skin for insulation.
Body water also varies from person to person relative to leanness or fatness. Age, hydration, and health status are also factors in determining percentage of body water.
Bone, the mineral mass of the body, is only about 4% to 6% of the body mass.
Body water is also determined by how long it's been since you've been in the bathroom.
Section C, causes of obesity and metabolism.
Obesity is associated with an increase in the size and/or the number of fat cells. With fat loss, the fat cells shrink in size, but the total number of fat cells is not reduced. Thus, people with extra fat cells are more prone to obesity. Although weight gain is usually associated with middle age, fat cell increase is most rapid during late childhood and early puberty. So maintaining a healthy body weight during these periods may be beneficial in controlling obesity later in life.
Genetics is an important factor in establishing a person's body weight and composition, tendency to gain weight, and the way energy is used. The level of the enzyme lipoprotein lipase, the enzyme which promotes fat storage, may be another important genetic influence.
Have you ever seen someone go on a diet, lose 10 pounds, and soon gain it all back? Well, there's a theory on why the body often gains back weight loss after dieting. It's called the set point theory.
According to the set point theory, when a person goes on a diet to lose weight, the body adjusts its metabolism in order to return to the initial heavier weight. It's as if the body has memory of the heavier weight and wants to return to it. Set point also refers to when someone tries to lose a certain amount of pounds, but can only lose so much and no more. This, however, is only a theory, because there's no known gene or physiological process that scientists have been able to identify that explains it. It's also a known fact that sometimes people lose weight too fast and end up losing mostly water, not fat, so they gain it back again.
There are 4 basic factors that are identified as true scientific explanations that may contribute to obesity: genetic metabolic, psychologic, social, and physiologic.
First, genetic metabolic factors linked to genetics are believed to have the biggest influence on becoming obese. There is something called the RMR, which refers to a person's metabolism. RMR stands for resting metabolic rate and is considered a contributor to, not a cause of, obesity. People with a low RMR are more susceptible to the development of obesity.
Psychologic factors are sometimes believed to be a contributor to obesity. The theory is that obese people eat when food is around instead of just eating when they're hungry, or obese people eat when they're going through a stage of unhappiness, or because they connect food with maternal love or as a reward. Basically, this theory says that obese people are eating in response to psychological or emotional questions and not in response to hunger.
Next, social factors contributing to obesity can range from socioeconomic factors to job environment. Often, obesity can be influenced by the eating habits of family and friends.
And finally, physiological factors that contribute to obesity are those that increase the size or number of fat cells physically present in the body. Physiology includes all the ways the body handles energy, such as energy efficiency, formation of fat cells, caloric intake, diet composition, and inactivity. Once these physiological changes happen, the only way to reduce weight is to reduce fat cell size.
All of these factors can contribute to a person's tendency to be obese. Now that we got that down, let's look into how weight gain and weight loss are affected by imbalances of energy in the body.
Weight loss and weight gain are a result of energy imbalances over a period of time. That is, when we equally expend energy in proportion to our food intake, we maintain our weight.
A pound of body fat stores about 3,500 kilocalories. However, just because someone consumes 3,500 kilocalories doesn't mean they'll gain a pound. And just because someone expends 3,500 kilocalories doesn't mean they'll lose a pound either. You know why? Because all calories are not created equal.
Here's a simple concept to keep in mind when discussing energy. Energy is provided by the foods and beverages we consume. Well, now isn't that simple? Calculating a food's caloric value, however, is a little more complex. If you know a food's carbohydrate, fat, protein, and alcohol makeup, you can figure out its caloric value.
1 gram of carbohydrate equals 4 kilocalories. 1 gram of fat equals 9 kilocalories. 1 gram of protein equals 4 kilocalories. And 1 gram of alcohol equals 7 kilocalories. Once you know these figures, all you have to do is multiply and add.
There are 3 factors that affect how the body expends energy. The first and foremost way is through your basal metabolic rate, which we'll explain in a moment. The second factor is physical activity, and the third factor is the energy released from food consumption.
Most of the energy people expend occurs during quiet metabolic activities like breathing, pumping the heart, those kinds of things. The basal metabolic rate, let's call it the BMR, is the rate of energy used for vital body processes.
The BMRs for men and women vary slightly. The BMR for the average woman is about 0.9 kilocalories per kilogram of body weight per hour. For men, it averages 1 kilocalorie per kilogram of body weight per hour. There are several factors that affect BMR: age, height, rate of growth, body composition, fever, stress, environment, fasting, starvation, malnutrition, hormones, smoking tobacco, caffeine, and sleep. You name it, and it probably plays a role.
Physical activity is the second influence on energy output. The frequency, intensity, and length of time of the activity, known as the FIT theory, influences the rate of caloric expense.
The third influence on energy output is the energy released from food consumption. That's right, you actually burn calories while you're consuming them. This is known as the thermic effect of heat, or the specific dynamic action of food. This specific dynamic action thing occurs when you eat food and heat energy is released from the body. It only accounts for about 5 to 10% of the total energy output.
Okay, let's take a quick look back at obesity and energy to make sure we've got it. There are 4 basic factors that are identified as explanations of obesity: genetic metabolic, psychologic, social, and physiologic factors. There are 3 factors that affect how the body expends energy. The first and foremost way is through your basal metabolic rate. The second factor is physical activity. And the third factor is the energy released from food consumption.
So no one thing causes obesity, but a number of factors do contribute to it. In this way, obesity has a lot in common with 2 eating disorders, anorexia and bulimia.
Section D, eating disorders.
An eating disorder is a clinically diagnosable disease. The eating disorders anorexia and bulimia are both characterized by an obsession for thinness and an overwhelming fear of becoming fat or gaining weight. Some behaviors of an eating disorder patient include going for days without eating, consuming only minimal portions of food to survive, maybe a strawberry for breakfast, a few leaves of lettuce for lunch, and then a cup of soup or broth for dinner, and exercising for hours a day in an effort to lose weight.
Anorexia is a difficult disease to deal with for several reasons. First, since our society values dieting and exercise, the anorectic, which is a person with anorexia, may first get support for her extreme behavior. Even when the disease becomes apparent to the outsider, comments like, "You're really looking thin, are you getting enough to eat?" support the anorectic behavior, because the fact that you notice the weight loss is complementary to the anorectic.
Second, anorexia is a secretive disease. The anorectic shies away from social environments where there is food. Often they wear baggy clothes to conceal their bodies and lie about their eating habits.
So how do we help an anorectic?
Well, the best thing to do for an anorectic is to show your love and support, but not to reinforce their anorectic behavior. For example, rather than drawing attention to their problem by saying, "You really look skinny, are you eating enough?" you should say, "You look weak and your face looks pale. Are you feeling okay?" As you show your love and concern for the overall well-being of the anorectic, they will slowly develop the trust in you to reveal the problem and seek the help they need.
The bulimic is different from the anorectic in that they have recurrent episodes of consuming large amounts of food in a short period of time. After their binge, they try to purge themselves of the food. For example, the bulimic may consume several thousand calories in only a couple hours, which is what most of us eat in a few days. After consuming these large quantities of calories, they try to reverse the eating by vomiting, taking a diuretic, or exercising for hours. The bulimic usually feels out of control during these binging episodes and feels helpless to stop. Most bulimics are of normal weight, so there's no noticeable physical signs for the outsider to pick up on.
For some reason, most anorexics and bulimics are women. We don't have a clear understanding of what causes bulimia and anorexia, but some experts think these disorders are brought on by the following.
1. Adolescent turmoil, where the adolescent has trouble developing an independent identity. 2. Controlling parents or a rigid family structure, where expression of feelings and ideas is inhibited. 3. Our society, where the female body is a sex symbol and commodity. And 4. A competitive environment, where slimness is emphasized.
Anorexia and bulimia are serious diseases. These eating disorders can cause severe medical problems such as heart arrhythmias, hormone disturbances, osteoporosis, and even death. But the good news is that they're curable. Treatment, however, is a slow process where the patient develops a new sense of identity and expression.
Now that we've taken a look at obesity, anorexia, and bulimia, let's talk about disease prevention through nutrition.
Part 7, Nutrition and Disease Prevention.
Diet is one of the many lifestyle factors that may influence the risk of developing a chronic disease such as cancer, diabetes, or heart disease. Unfortunately, the relationship between chronic diseases and diet are not a simple cause and effect parallel. It's not that easy. Although some diseases are caused by poor diets and can be corrected with adjustments, many are not and require other methods of cure and prevention.
I'm sure we all know people who defy good eating habits and yet live long lives. And there are others who lead healthy lives but fall victim to chronic diseases anyway. Diet, however, can influence the time of onset and ultimate course of certain diseases. The relationship of diet and disease is also influenced by other factors, such as genetics, age, gender, lifestyle, and environment.
Okay, now that we understand nutrition's role in disease prevention, let's look at how it actually works in our immune systems.
Section A, Nutrition and Immunity.
The immune system depends on the interactions and secretions of various organs and white blood cells. The immune system responds when a foreign substance penetrates the skin, the gastrointestinal tract, and/or the mucous membranes, which are the first line of defense against infection. In order to function well, the immune system must have nutrients available. Individuals who do not have sufficient nutrients in their systems develop more infections than well-nourished people do. It's as simple as that.
The mucous membranes are also compromised by a reduction in one type of antibody secretion. Since antibodies are proteins, a poor diet will inhibit protein synthesis due to a lack of essential amino acids and metabolic cofactors. Antibodies are normally produced by the immune system to fight invading foreign molecules. Failure to produce these antibodies can lead to lung and GI tract infections, particularly among children.
In addition to antibodies, nutrition affects the cells of the immune system. The system depends primarily on 3 types of white blood cells to defeat infections. They are phagocytes, T cells, and B cells.
Phagocytes are white blood cells that literally eat other invading cells by engulfing and digesting them. This process is called phagocytosis. Lack of nourishment delays the kill time of phagocytosis. Other white blood cells are lymphocytes, either T cells or B cells. T cells are stored in the thymus gland for a period of time. They also reside in the lymph nodes, spleen, bone marrow, and areas lining the GI tract. T cells then travel to meet and fight the foreign molecules. These foreign molecules are called antigens. Common forms of antigens are bacteria, toxins, and viruses.
What's so incredible is that although there are millions of different antigens, each T cell can only attack one type. Every time a new antigen is introduced to the body, a new T cell is made to fight that antigen and that antigen only. That's why vaccinations are made up of the very antigens we're trying to protect ourselves against. T cells defend against fungi, viruses, parasites, and some bacteria. They are also capable of destroying cancer cells. Malnutrition affects T cells significantly because the number of circulating T cells is reduced.
With malnutrition, the thymus gland, lymph nodes, lymph-associated areas of the intestinal tract and spleen are reduced in size, leaving these T cell areas depleted of lymphocytes.
Malnutrition affects the other type of lymphocytes, B cells, to a lesser extent. B cells respond to invading organisms by producing antibodies known as immunoglobins. Circulating immunoglobulin levels seem to remain normal regardless of nutrition, but the actual antibody response may be impaired.
Now let's look at some diseases associated with or affected by nutrition.
Section B, Diabetes, Type 1 and Type 2.
There are 2 main forms of diabetes mellitus. Type 1 is called insulin-dependent diabetes mellitus, IDDM, and is less common than Type 2, called non-insulin dependent diabetes mellitus. Only about 20% of the people with diabetes have type 1 diabetes.
Someone with type 1 diabetes produces no insulin at all. The pancreas loses its ability to synthesize insulin. Insulin is responsible for a lot of things, not the least of which is the uptake of glucose from the blood. Without insulin, blood sugar levels get dangerously high. In order for the cells to take up the glucose from the blood, the diabetic must take insulin injections. Type 1 diabetes is also known as juvenile onset diabetes, although some cases may occur in adults as old as 30 years of age.
Someone with type 2 diabetes produces a small amount of insulin, but not enough. Type 2 diabetes is much more common. Insulin is still produced, but the body's cells resist it. This type can sometimes be controlled by diet alone. If that does not control blood glucose levels, the person may take insulin or insulin-inducing agents to increase the body's supply. These agents are known as oral hypoglycemic agents.
So, some people with non-insulin-dependent diabetes mellitus do take insulin, although from the name you would think that they didn't. That's why it may be easier to remember it as type 2 diabetes.
A common myth associated with diabetes is that dietary sugar is its cause. That's baloney. Fact. Controlling sugar intake is a part of the treatment of diabetes, but sugar does not cause the development of diabetes. The major health problem associated with eating too much sugar is tooth decay, not diabetes.
Sugar can contribute to the onset of diabetes only in the sense that it may also contribute to obesity. Scientists aren't completely certain what causes diabetes in all cases, but obesity may increase the chances of activating a pre-existing gene for diabetes. For the most part, a diet rich in complex carbohydrates and fibers and low in concentrated sugars does help regulate blood glucose. Even a diet low in sugar won't prevent diabetes if the gene runs in the family.
Do you remember the exchange system that we talked about earlier? Well, diabetics, for whom the exchange system was first developed, often still use it to plan their meals.
Now let's talk about one of the scariest diseases connected to poor nutrition that can be avoided with a healthy diet: atherosclerosis.
Section C, atherosclerosis.
Atherosclerosis is the accumulation of lipids and other materials in the arteries. It is characterized by a buildup of lipids along the inner walls of the arteries.
Everyone has some degree of atherosclerosis. It usually begins with the accumulation of fat along the inner walls of the arteries. When this happens, the buildup is called plaque. Over time, this plaque hardens, which stiffens and narrows the arteries. This causes a rise in blood pressure, which further damages the artery walls. The heart has to work harder to pump the blood through the narrowed and hardened arteries.
It's possible to fight atherosclerosis by reducing the amount of fat in your diet, especially saturated fat. A healthy diet has a total fat intake that is less than 30% of total kilocalories consumed. Saturated fatty acids should only comprise 1/3 of that total, with dietary cholesterol less than 300 milligrams per day. This type of diet may help lower blood cholesterol levels by 5 to 10%.
Cholesterol is carried in the body by several lipoproteins. The two referred to most frequently are high-density lipoproteins, HDLs, and low-density lipoproteins, LDLs.
LDL cholesterol is strongly associated with atherosclerosis. Thus, it is known as bad cholesterol. HDL is good cholesterol. HDL reduces the risk of atherosclerosis. In other words, you want low LDL and high HDL. Vigorous exercise may increase your HDL. Another way to remember this is HDL is healthy and LDL is less healthy. Increasing consumption of complex carbohydrates and fiber may also assist in lowering LDL cholesterol.
Be aware that for most people, consumption of cholesterol in their diets does not increase their blood cholesterol level, even though you have probably heard that repeatedly. It is actually the saturated fat that seems to increase the LDL. So, dietary cholesterol has a worse reputation than it actually deserves.
So why is atherosclerosis so bad? Well, we mentioned earlier that it causes high blood pressure. Chronic elevated blood pressure is called hypertension. It's a significant factor in strokes and heart attacks. People can't feel high blood pressure, so it's known as the silent killer. There are a number of diet-related factors that affect blood pressure. Excess body fat, especially abdominal fat, is one of them.
Weight loss is an effective method of treatment for hypertension. Regular, moderate aerobic activity, such as brisk walking, helps reduce hypertension both directly and indirectly. It strengthens the heart and blood vessels, increases lean muscle mass, reduces the workload of the heart, changes hormone levels, and improves the movement of blood through peripheral arteries.
Salt, sodium chloride, contributes to hypertension in some individuals who are considered to be salt sensitive. Avoiding salt prevents hypertension in salt-sensitive individuals, but may not help others with hypertension. We used to believe it was the sodium that increased blood pressure, but recent research indicates it may actually be the chloride, as in sodium chloride, that causes the problem.
However, most people will not develop hypertension from excess salt consumption. Salt, like dietary cholesterol, is not as great a health risk for most people as is commonly believed.
Some research indicates potassium may help prevent and correct hypertension. Thus, increasing potassium intake may be helpful. Calcium is another mineral that seems to prevent and treat hypertension. This is another reason to at least meet the dietary recommendations for calcium. Consumption of low-fat or non-fat milk products is recommended because they provide calcium, potassium, and magnesium without all the saturated fat that comes with regular milk.
Those who regularly consume 2 or more alcoholic drinks daily have an increased risk of hypertension. And second, despite all of this, the relationship between a high-fat diet and hypertension is not clearly understood at this time. But overall, remember this rule of thumb. Healthy eating makes for a healthy living.
Section D, nutrition and cancer.
Nutrition and cancer are related in more than one way. Food may contain carcinogens, substances that initiate cancer, but food may also contain substances that protect against cancer. For folks with cancer, proper nutrition may facilitate recovery and improve quality of life. Food additives have a bad reputation for causing cancer, like dietary cholesterol and salt. However, food additives are probably blamed for problems they did not cause.
The development of cancer is usually a long, involved process over time. Dietary fat is associated with cancer in animal studies, but research does not indicate it causes cancer in humans. Dietary fat appears to promote the growth of cancer after exposure to a carcinogen. Certain forms of fat seem to have this effect more than others.
For example, omega-3 fatty acids and monounsaturated fatty acids don't seem to facilitate the growth of cancer. But linoleic acid, the polyunsaturated fatty acid of vegetable oils, does seem to increase cancer growth. The research is not definitive yet.
Dietary fiber may reduce the risk of certain cancers, particularly colon cancer. This may be because fiber decreases the length of time the colon is exposed to carcinogens, or it may be because it speeds the excretion of foodstuff from the body. In general, a diet that is low in meat products and high in vegetable and grain products is associated with lower rates of cancer. Yellow and green vegetables and fruits seem particularly effective in protecting against cancer. The American Cancer Society recommends 5 fruits and vegetables a day.
While there is great debate over which substances actually help protect against cancer, beta-carotene, vitamin C, and vitamin E, known as the antioxidants, seem the most likely prospects at this time. Pills containing these substances do not seem to have the same effects as the vegetables and fruits themselves. The research indicates that those who eat a variety of vegetables and fruits in generous quantities have reduced cancer risk.
But realize that smoking, alcohol, pollution, and genetics may all contribute to the risk of cancer. You may also want to avoid potential carcinogens by reducing your consumption of foods preserved by salt, smoke, or nitrates.
Everybody needs food and nutrients, right? So if you and I know that, then businesses know it too. We have to be careful when we buy health foods and supplements. Let's look at some general guidelines that can help you make wise decisions about nutritional products and claims.
If it sounds too good to be true, it isn't true. Watch out for these 8 things when considering purchasing supplements and nutritional aids. First, simple solutions to complex problems. Forget about it. Most of us want a quick, miraculous cure for our problems. But in reality, there just aren't any simple solutions to complex problems. Second, logic without proof. The claim seems to be based on sound reasoning, but it hasn't been tested scientifically. Third, unpublished studies. Scientific studies are cited, but are nowhere to be found, or if they are published, they're published in a non-scientific journal, magazine, or newsletter. Fourth, testimonials. Evidence presented to support the nutrition aid claim is from individuals who claim to have been cured or received the benefits of the product. Don't be fooled. These people usually get paid to make these testimonials. Fifth, product dependency. Look out for attempts to make you dependent upon a product. Other than impending medical conditions, good nutrition can be achieved through a healthy diet. 6. Salespeople who pose as nutrition experts. Different states have different regulations on who can call themselves a nutritionist. Some states don't have any regulations. 7. Businesses that fail to inform clients about risks associated with using their product. Ask yourself and them, are there any physiological risks or health risks? And the 8th thing to look out for when buying supplements and nutritional aids, businesses that require you to spend large amounts of money or sign ongoing contracts for their service or product. Other than a chronic condition, health and nutrition can be achieved fairly cheaply, and that's it.
Well, that just about covers it. We hope you've enjoyed the nutty, nougat-filled world of human nutrition. Please be sure to check stores for other videotapes in the Standard Deviants series on topics such as astronomy, anatomy, and physics. If you have any questions about this videotape, or if you just want to chat about eating healthily, feel free to call us at 1-800-238-9669. We'd love to hear from you. Thanks for choosing the Standard Deviants. We hope you had a healthy dining experience.
Step right in, step right in. Go tell all your friends. You got all that fatty nutrition knowledge, it percolates within. Now let your mind do the rewind, my concubine. Let this list refresh your mind. Food choices in human health, nutrition standards and guidelines. The remarkable body. Hey baby, you look so fine. Carbs, lipids, proteins and vitamins, minerals, water, give energy within. Balance, weight control, nutrition and disease prevention.